Hello everyone. So I'll be talking about using different machine learning techniques to boost the Higgs-top CP measurement at the LHC. But before delving into the main presentation, let me take a moment to acknowledge let me take a moment to acknowledge the many significant works by Professor Rohini over the past several decades on understanding the Higgs CP structure. And in this slide, I have listed only a fraction of those papers. These studies incorporated and they introduced several key CP observables which play a central role in several ongoing studies, several experimental studies and pheno studies. And many of these observables and approaches have also been incorporated and adopted into my own studies that I'm going to talk in this presentation. Now, my collaboration with Professor Rohini was on a somewhat different topic. I collaborated with Professor Rohini along with Biplab, Genevieve, Amandeep, who are in the crowd, alongside Ritaja, Deepan, Amit, on probing the light neutrino parameter space in supersymmetric models. I'll have a short overview of those topics at the end of the presentation, and Genevieve also covered some of these topics today in her talk. So with this tribute in mind, let's dive into the main presentation. So new sources of CP violating interactions can be crucial to explain the matter-antimatter asymmetry in the universe. And one such exciting prospect is CP violation in the Higgs sector, which can be realized through a mixing between CP even and CP odd states. Now, the pure CP odd hypothesis has been excluded at the LHC, but the mixed hypothesis is still allowed by the current data. Now, CP violation in Higgs gauge boson interactions have been extensively tested at the LHC, but these interactions can be loop suppressed. On the other hand, CP violation in Higgs fermion couplings can manifest directly at the tree level, making them more natural or more sensitive probes. And among the Higgs to fermion couplings, the largest is the Higgs-top interaction, making it a desirable candidate to perform new physics studies. Now, the Higgs-top interaction can be parameterized to this Lagrangian, where the standard model sector can be retrieved by setting kappa t to 1 and alpha to 0. So the question is, a precise measurement of this CP structure could, in principle, help in unraveling the clues for new physics, which we target in our work. Now, this Higgs-top CP structure can be directly accessed at the LHC through searches in the TT-bar Higgs channel. Now, despite a relatively smaller cross-section, where it is roughly 100 times smaller than the in the gluon fusion-induced single Higgs production channel, it does feature a very rich phenomenology. And both the CMS and ATLAS collaborations have reported observation in the standard model TT-bar Higgs channel with greater than 5 sigma, and through searches in the TT-bar Higgs with Higgs going to gamma gamma, the ATLAS collaboration has excluded the Higgs-top CP phase up to 43 degrees at 95% confidence level. Now, various different CP observables have been introduced in the literature previously. So in this work, in a previous work, we tried to look into the different or the amount of CP information that is present in these different well-motivated CP variables. So the diagonal entries here represent the amount of CP information present in these observables relative to the full information that is present in a machine learning network that was trained on a combination of all 8 observables. So here we see that the highest amount of information is contained in delta eta TT bar, which is the pseudo-rapidity difference between the top and the anti-top. Also, we have theta star, which represents the Collins-Hopper angle. So this is the angle made by the top quark with the beam direction in the TT bar rest frame. Similarly, the off-diagonal entries represent the amount of CP information contained in a 2D correlation of 2 observables. And here we see that the combination of delta eta TT bar with the transverse momentum of the Higgs boson results in a high amount of CP information. Likewise, the combination of theta star with mTT bar Higgs, which is the invariant mass of the TT bar Higgs system, also results in a high amount of CP information. So the goal of this exercise was mainly to show that the amount of information increases with successive addition of observables. And this illustrates the necessity of performing a multivariate analysis. Now, one can also define genuine CP sensitive observables which carry sensitivity to the sign of the CP phase. And this becomes possible due to the short lifetime of the top quark, and which allows it to decay before its hadronization. And therefore, the spin correlations between the top and the anti-top, which in principle gets modified due to the Higgs-top CP structure, can be traced back from the decay products of top and the anti-top. And in the TT bar rest frame, one can then define these azimuthal angle differences between ij, where I and j are the decay products for the top and the anti-top. And in these observables, we do see a sensitivity to the sign of the CP phase as well. So here again, we use the Fisher information metric to look at the amount of CP information that is present in different delta phi ij's constructed between different decay products. And here we see that, for example, if we take the case of the dileptonic TT bar Higgs channel, the highest amount of spin information or CP information is contained in delta phi constructed between the charged leptons. Similarly, the second in line is the one constructed between the charged lepton and a bottom quark. And if we take the ratio of the CP information between these two, it correlates with the spin analyzing power of the bottom quark with the charged lepton. So, with these various observables at our disposal, we attempt to further enhance the extraction of new physics information from these observables using some machine learning techniques. And I'll go through two such techniques. So, in the first part, I'll talk about a machine learning based likelihood inference approach. And in the second part, I'll introduce a normalizing flow based unfolding model which can be used to map observed data or the data at the detector level directly to its parton level phase space. So, a typical collider analysis involves a comparison between events that are measured at the LHC with the events that have been simulated, assuming some new physics hypothesis. And the first step in the forward theory-based event simulation chain is typically the generation of events at the parton level, followed by hadronization, showering, and then a simulation of detector response. And the event information that is obtained at the end of this forward simulation chain is then compared with the events that are measured at the LHC. Now, in an ideal world, if the likelihood function would have been known, where the likelihood function represents the probability of observing events x at the detector level, given the theory parameters theta, which in our case are alpha and kappa t, if this likelihood function was actually known, then we could have easily mapped any measured data into the theoretical parameter space. Similarly, it would allow us to define the likelihood ratio, which is known to be a powerful test statistic to parameterize any potential deviations from standard model. But in a realistic scenario, its computation can be quite involved. So, in this case, we see that in order to compute the true likelihood function, one needs to integrate over the various latent parameters that in principle convolute the data or convolute the simulation chain. And due to the large number of latent variables involved in this computation, it becomes intractable. So the question is, can we somehow estimate or guess the true likelihood function? And the short answer is yes. So the integrand of the true likelihood function is a latent variable dependent likelihood. And the first term here is the parton level event likelihood, which can be computed for every simulated event. Now, using this idea, one can define this joint likelihood ratio, which is basically a ratio of the latent dependent likelihood at theta and a reference theta Sm. And this boils down to a ratio between the parton level event likelihood, since all the latent dependent terms cancel out. So one has the joint likelihood ratio, which can be computed for every simulated event. And using this information, one can define loss functions of this form, which was first introduced in 2018. And it was found that the minimizing function of these loss functions in principle become the true likelihood ratio. So this whole problem basically boils down to a minimization problem, which can be tackled using machine learning networks. So once this network is properly trained, the trained network essentially becomes an estimator of the true likelihood ratio. So using this methodology along with the various CP observables that have been suggested in the literature, we derived the projection contours in the plane of alpha and kappa t for HLLHC, and we found that the Higgs-top CP phase could be probed up to 13 degrees at 68% confidence level at the high luminosity LHC. Now, while this likelihood inference technique is able to directly learn and parameterize the intractable likelihood function, resulting in improved inference, we must also address the fact that this technique accesses measurements only at the detector level. And the detector level observables in principle do have convolutions of their own. So for example, if we compare the Collins-Hopper distribution between the parton level and the detector level for semi-leptonic TT bar Higgs, we see that there is roughly a 40% reduction in the amount of CP information at the detector level. So this motivates us to look for alternate methods where even these limitations could be overcome. And likewise, the events that are typically measured at the LHC, they are also convoluted by detector effects, by other uncertainties. So there is a need to remove or get rid of these convolutions in order to perform a precise comparison between theoretical predictions and the measured data. And this brings us to the idea of unfolding, which is basically a procedure to correct these convolutions. So unfolding allows us to reconstruct the full parton level phase space from the measured data or from the detector level data, thus allowing us to compare new physics hypothesis right at the parton level where the new physics effects are expected to be maximum. So various different classical unfold. So my main goal is, for example, just to remove or get rid of the convolutions that in principle could be introduced by the detector level simulations, or the convolutions that are in principle. Oh, I'm sorry, I should have been more clear. So by parton level, I refer to the hard scattering level. So after the partons have interacted, I do have produced the hard scattering level final state particles. So I'm trying to produce the final state particles, the 4 momenta of the final state particles after the hard scattering of the partons, before the hadronization, showering, and before the detector simulation. I mean, it's a well-defined, it's a different, yes, the particle level object. Parton level cross section here. It's a differential cross section basically. We can talk about. We can talk about this later. I mean, the truth level information base, exactly. Yes. So the main goal, the key point here is that at the end of the day, I'll compare the generated truth level distribution and the true truth level distribution, or the simulated truth level distribution. My goal is to match these two. Yeah, and various different classical unfolding techniques have been explored in the literature, but these techniques are typically limited to 1 or 2 dimensions. Therefore, a full phase space reconstruction at the parton level is not feasible. Also, these techniques are typically bin dependent, which can make them statistically unstable. So, generative machine learning techniques do allow us to construct these bin independent and high dimensional unfolding models. Now, 2 such generative ML techniques have been explored previously, but these techniques displayed a large training bias. Or in other words, the performance of these networks start dropping down whenever there is a statistical difference between the training dataset and the test dataset, which may not be an ideal scenario when we are trying to perform an inclusive analysis. Now, alternatively, normalizing flow-based invertible neural networks have shown a tremendous potential, and these enable a fully invertible and high-dimensional probabilistic mapping, as we'll see in the next few slides. These also avoid the limitations that are in principle present in the previous 2 methods. So we develop a new unfolding model using this particular technique. Now, the normalizing flows are basically a series of bijective transformation layers that map a complex probability distribution to a simple probability distribution. And these transformation layers are defined in such a way that they have a tractable Jacobian, which allows the input and the output densities to be mapped exactly and also in the reverse direction. So this is just a schematic representation of how we perform the training. So we start with the simulated parton level distribution, or the true parton level distribution. And this is mapped to a random vector space. Similarly, in the reverse direction, a latent vector space is mapped to a generated parton level data, which is supposed to be the output of my unfolding model at the end of the day. And this mapping is performed conditional upon the simulated detector level information. So once this whole network is trained, the data that is measured at the colliders, or the detector level data, will be given as a conditional input, and this network will churn out the generated parton level distribution, and it is trained in such a way that the loss function, or it could be a mean square error loss, or it could be a likelihood loss between the generated parton level and the simulated parton level, is minimized at the end of the day. So let's take a look at the problem that we try to solve with this. So we try to apply it to the semi-leptonic TT bar Higgs channel, where the parton level is characterized by 8 particles in total. These 8 particles could be in principle be parameterized by 22 degrees of freedom. But the detector level here has additional complexities. It can have additional QCD jets. There is missing degrees of freedom due to this neutrino. And also, to keep things inclusive, we adopt an event selection where we choose exactly one isolated lepton, exactly two isolated photons, two BTAC jets, but we choose up to 6 light jets at the detector level. So at the detector level, we have 46 degrees of freedom parameterizing this whole event. So our goal is to map this 46 degree of freedom to 22 degrees of freedom and also map it in a probabilistically faithful way. So the first question is, can we reconstruct these two light jets, the top quark and the anti-top quark at the parton level from a variable number of jets at the detector level? So basically this boils down to the question of resolving the combinatorial ambiguity in the jets. The second question is whether it's able to reconstruct the full phase space. So we are training the network using certain variables, and we do expect that the network will behave nicely when it comes to these distributions. But if you're using the network to generate some observables which has not been given us in the training input, then how does it perform? And thirdly, we also check how biased the unfolding model is. So to answer the first question, it seems that the model is actually able to resolve the combinatorial jet combinatorial ambiguity quite nicely. And to see this, I mean, we can look at the distribution of the invariant mass of the top and the anti-top at the parton level. So here, the dash distribution corresponds to the true parton level distribution, or the simulated parton. The simulated parton level distribution, while the solid lines correspond to the distributions that are generated by the network. So here, the distributions in red correspond to the data set where we have included up to 6 light jets at the detector level, and the distributions in green are those which have exactly 2 light jets at the detector level. So it's relatively more easier for the network to figure the green data set out. But in both the cases, we do see that over the bulk of the phase space, there is a good match between the two. I mean, both of them roughly match within 10 to 15% over the entire kinematic region. We can also take a look at the invariant mass of the hadronic top, and there also we see that there is a good match between the CINN generated distribution and the true parton distribution in the majority of the phase space. The second question was whether it's able to fully reconstruct the full parton level phase space. So here we show the distribution of Collins-Hopper angle at the parton level. This angle was given as input to the network during its training. So we expect that the network should behave very nicely and its output should match very well with the true parton level, and that actually happens. But delta phi tt is something that the network had never seen before. But despite that, it seems that the network is able to reproduce the parton level truth with a good amount of match to the true parton level distribution. And finally, to test model dependence, what we do is we train 3 different models. The first model is trained on TT bar Higgs events generated with the Higgs-top CP phase of plus pi by 4. Model 3 is trained on TT bar Higgs events generated with the Higgs-top CP phase of minus pi by 4. And model 2 is trained on standard model TT bar Higgs. Now, we use all 3 models, which were trained independently on different data sets, to unfold the standard model TT bar Higgs. So what we want to see is whether the output distributions resemble the test data set, which is the standard model TT bar Higgs, or whether it resembles more with the training data set, which is different for model 1 and model 3. And let's look at the results here. So here again, the dashed lines correspond to the true parton level distribution, or the simulated parton level distribution. These flatter contours correspond to the cases where pi is equal to plus pi by 4 or minus pi by 4. So model 1 and model 3 was actually trained on these distributions. Now here in the background, there is this green dash distribution, which is the standard model TT bar Higgs. So we are trying to unfold this distribution using models that were trained on these flatter distributions. The output from the network is shown through these solid curves, and we see that in all the 3 cases, the network has a closer resemblance to the test data set than the training data set. Now, of course, there is bias, there is a lot of bias, but we see that this bias is still lower compared to the variations in the parton level truth when alpha is varied. And yeah, with this I conclude my talk. So to summarize, we see that the CINN based unfolding model was able to restore the true parton level information to a good extent from a convoluted detector level distribution with additional QC digits. And of course, there are certain biases and there are uncertainties which still need to be improved. It also avoids a very large model dependence, and it allows the reconstruction of various well-motivated CP observables at the parton level where the new physics effects are maximal, and this allows us to compare the hypothesis at the parton level. And it provides an exciting potential for precision measurements and new physics searches in the era of high luminosity runs. And before completing, let me again acknowledge Professor Rohini. So, as I mentioned earlier, we collaborated on light neutralino dark matter in the supersymmetric models, along with Biplab, Genevieve, Amandeep, Ritaja, Deepan, and Xerxes, and Amit. And it resulted in several papers, and it was a great learning curve working with her. And it's a great honor to be able to talk in this memorial conference for Professor Rohini. Thank you.